Right, this is the easiest and the most important of electricity. This is capacitors. Capacitors are a device for storing charge. They store energy electrically, which makes them different from a battery that stores it chemically by a chemical change. They're also much quicker at releasing their charge, quicker at releasing energy. Here you have a standard capacitor, usually drawn like this because the early ones were parallel plates, two plates parallel to each other with a gap in between. And the idea is that electricity on one plate creates a dipole at the opposite on the other plate. So the electrons on the left-hand plate drive away the electrons from the plate facing it, so there's only positives. This creates a charge storage. Now when you allow the charge to run away from here, it runs away really quickly. So you charge a capacitor by simply connecting it to a cell battery power source. Electricity in the form of electrons run round the circuit until there is a charge difference created across the capacitor, at which point the current stops flowing and stops. There you are. That's a charged capacitor. Now the capacitor is charged, there is no current. There, you have a charged capacitor. Now, when the capacitor is charged and the current is stopped flowing, it stores the charge. You can disconnect it. It will continue to store the charge. Of course, some of it will leak away. But in order to explain it properly, so this circuit basically can explain all the... we need this circuit. This circuit has the two-way switch in the top, which explains everything. Now, I'm going to attempt, and I'm probably going to do it rather badly, to explain how the thing works. Now, of course, it's not connected at the moment in the charging. It's in a discharge form. If we want to connect it to charge, we have to connect it here and disconnect this one here. At this point, it charges. Then we disconnect this one and charge this one, and the capacitor will discharge through the lamp, and the lamp flashes because the current all flows very quickly off at once. This is the circuit for a camera flash. You charge it up by connecting it to the battery and discharge it by connecting it to the lamp. The two resistors here, as you can see, this resistor and this resistor, are protective resistors, which are meant to stop too much current flowing, which will damage the battery or the lamp. Right, now the construction of a parallel plate capacitor basically looks like this. Essentially, you're sandwiching two metal sheets, and between them you're putting what's called a dielectric. This is a material which doesn't conduct electricity, but is very good at the transfer of electric fields. The electric fields find it easy to express themselves within this material, and this material is called a dielectric. Now, the formula you see at the bottom is for the parallel plate capacitor. You don't have to remember it, it's in the logbook. So, how do you use a capacitor? Well, you use a capacitor in a camera flash. Now, I have warned quite a lot of you, and quite often, that you have to be more specific about what you're saying for a use. You cannot say a camera. You have to say a camera flash. You cannot say in cars. You have to say hazard lights in cars. And you cannot say in rectifiers. You have to say smoothing rectifiers, which we do in semiconductors. So, a capacitor, as I just said, can be used to smooth the output of a rectifier. This is a bridge rectifier I'm showing you here with the 4 different diodes. As you can see, there's 2 versions of it. But basically, you are taking a signal which looks like the first diagram there. That's the input. And you're turning into this as output. Now, if you get the capacitor right, it doesn't go into this sawtooth shape, it goes nice and flat. So you tune the capacitor to smooth the output of a rectifier to give you direct current. Here we have a variable capacitor. The variation in capacitance is achieved by changing the area of overlap. If you twist the knob, The little fins move in and out from between them each other, and it changes the amount of overlap. If you change this area of overlap, you're adjusting the size of the capacitor. This is used to tune radios to different frequencies, to tune the area so it's receptive to different frequencies. Not for amplitude, but for tuning. And here are capacitors used as smoothing inside a radio. The large array of capacitors does the job more effectively than one. The actual rectifier is there. That's the rectifier, 4 little diodes, and each of these capacitors works on a slightly different frequency so that you get, no, I really do mean slightly different, and so you get a really nice smoothed output which then is used in the radio. So it comes in to the transformer where it's turned into the voltage you require, usually 12 volts, 6 volts, something like that. Only then can we rectify it, because of course you have to have alternating current to pass through the transformer, and then it's rectified to DC when it's at the correct voltage and then powers the radio. Okay, so factors that affect a parallel plate capacitor, we've already discussed them briefly, but let's do them in slightly more detail. Distance between the plates, further they are apart, lower the capacitance. Area of overlap, and this is the area in which they're literally facing each other, and the variable capacitor changes this. It slides the plates up and down. And the material between them, in this material called a dielectric. Now, the permittivity, which is this strange little E you may see on the screen, this permittivity, there it is, that's usually a multiple of the permittivity of free space. So often in a question, they'll count the relative permittivity as, say, 4. This means that in the calculation, the permittivity is the permittivity of free space times 4. So you're given a permittivity relative, and it's always a multiple. So you look up E0, which is in the logbook, and use that times 4. And a dielectric, usually some sort of plastic material, which separates the plates so they can be very close together and yet separate, and also increases the permittivity of the area between them. Okay, so this is the formula I was just talking about. That's it all written down. Area, permittivity, distance makes capacitance. The units are farads, should be Faradays. That's the French's fault. They don't like the idea of 3 vowels. They not happy with English scientists generally having things named after them. Faraday, easily the most important person in the history of electricity, gets his name truncated to Farad. Nice. So we can do simple questions. That's all the details there. You can just pause it and go through it. I'm not going to waste your time with it. We can also use this formula. Guess where you find this formula? Yes, it's in the little book. That's right. Look up the formula, use it. What sort of use it? Well, you get this sort of a question. They give you the charge. There's the charge up there. They give you the voltage, and they ask you for the capacitance. Well, charge is always written as Q, voltage is V, capacitance, unsurprisingly, is C. You're looking for a formula in the logbook which connects Q, V and C, and there it is. And you just use it. You might have to do a bit of manipulation, but you basically just use it. Get used to using it. Final one is the energy stored, which is probably the one most asked because it pops up most often in question 5s and always comes in as there's a question 12 on the subject. The amount of energy, how useful a capacitor is, how much energy it will store. That's, as you can see, a half CV squared. V is the voltage, C is the capacitance. Now, the energy you store in a capacitor is also the work you need to do to charge it. They're, of course, the same thing, so that there's it can be kept together. You know, the whole, like, you know, physics can be kept together. You know, this third law business, all this, like, you know, not destroying energy, all that kind of stuff. So that's that. Now, combination questions. So this one is a combination question. First, they are getting you to work out what the actual permittivity is. There it is. This one, they've said the relative permittivity of 3. So you times the permittivity of free space by 3. That's, of course, from the logbook. It gives you the area and the distance and asks you for the capacitance of a parallel plate capacitor. So you work it out. It's in farads. Then, energy stored, you use the capacitance from the first section and the voltage, which is also in the question somewhere, there you are, the voltage, which is also in the question, to give you the energy stored, either the energy stored or the amount of energy needed to charge it fully. Finally, in this section, we have to look at electric field lines. Electric field lines are the lines that an electric charge would go if it was allowed to move freely. Between a parallel plate capacitor, they're straight. Some of you might remember this if you do chemistry from Millikan's oil drop experiment. A uniform electric field can be created between the plates of a parallel plate capacitor. I'm really pleased getting that sentence out with only the one stumble. So that's the shape of the field. Other fields you might try to create. There are 2 more fields. You can see this one looks like a magnet. Can you see that? Looks like a magnet. As every field looks a bit like a magnet, it's a field, magnet, a field. That one looks like a north and a north placed together in a magnet. So they are magnetic type fields. They look very like it. They have the same kind of shape. Obviously, maths works in only the one way. And the way we reproduce it is we float some material, usually semolina, which is a sort of a part of a grain of wheat, which is often used in desserts, on top of castor oil or olive oil, which is an insulating material. And when we have a very, very high voltage field, you create with a huge voltage, I'm talking about thousands of volts, and you place them like this, the semolina will form a dipole and will line up with the electric field. So you can see the electric field. Now, this is an incredibly dangerous experiment, and I've given myself once an enormously nasty shock, so you won't be seeing me do it anytime soon. Now, batteries are not capacitors. Batteries, cells which store their energy or produce energy from chemicals, from a chemical change. There are basically 3 types. Your wet, rechargeable, like in a car, lead, that's basically lead plates in acid. You've got your dry cell rechargeable, nickel, cadmium, lithium. These are the typical metals they use. They use them in mobile phones, power tools, things like that. And then you have your dry non-rechargeable. These are your 20 in a pack from the pound shop. And they're zinc and carbon. On the right is a zinc carbon battery. The zinc is the outside layer and the carbon is the bar that runs down the middle. And between them, there's usually a manganese or something which produces the electricity, the chemical involved, as it were. So rechargeable batteries obviously better because you can use them many times. They are more expensive and more bad for the environment to produce in the first place, but when you throw them away, they're not so bad, or you shouldn't really throw them away. Very few people do, whereas obviously standard batteries get thrown away all the time. They're less expensive, but they really don't, not so good for the environment. So here's the question. There's lots of questions on capacitors. I could have picked loads of part questions, but instead I chose this long question from 2014, and I hope this one is of some help. Now, there's obviously other bits of this, including the polarization of light, but no harm doing revision as you go along. The questions tend to be more mixed up. As we move towards 2015, 2016, the questions mix subjects more readily. No problem with that, personally. You should be a master of your subject.